In this online lecture, we're going to continue with our introduction of nuclear chemistry. First, we're going to talk about the difference between chemical reactions and nuclear reactions. Next, we're going to predict radioactive decay based on the band of stability. And then finally, we're going to talk about the kinetics of radioactive decay and discuss half-lives. So there's a nice table in your book that discusses the difference between chemical reactions and nuclear reactions, and I just simplified it a little bit just to make it a little bit more succinct. So one of the biggest pieces is the conservation of mass. Chemical reactions, if you start off with 4 carbon atoms, you're going to end up with 4 carbon atoms, specifically carbon-12. You'll end up with 4 carbon-12 atoms. In nuclear reactions, a change in identity often will take place. As for chemical reactions, it's the electrons. Remember, it's the valence electrons that are participating in chemical reactions. In nuclear reactions, usually electrons aren't involved. It's mainly the nuclear particles, the protons, the neutrons. Sometimes in the electron capture, for example, a low-lying electron can be captured by the nucleus, but usually electrons are not involved for nuclear reactions. Chemical reactions, we have small changes in energy, conservation of mass. With nuclear reactions, remember we talked about E equals mc squared. We have these large changes in energy because of measurable changes in mass. And then for chemical reactions, reaction rates are influenced by temperature, concentration, catalysts, and the state of the compound. Whereas for nuclear reactions, the reaction rate really only depends on the number of nuclei. There are some exceptions, but nuclear reactions follow first order kinetics. So the rate just depends on the concentration of nuclei present. Quick review, components of the nucleus. So this nucleus has protons, neutrons, and then we have electrons that are in these clouds orbiting the nucleus. So when we write out a particular nuclide, a nuclide is a nucleus with a particular composition. Each isotope of an element has a different nuclide. So when we write out a particular isotope, we put the atomic symbol where X is here, like this carbon-12. A is the mass number. This is the total number of nucleons, which is your neutrons and protons. They're the particles that make up the nucleus. And then the atomic number is just the number of protons. So the identity of the element is determined by the number of protons. A particular nuclide is often designated by its mass number. So for example, carbon-12 and carbon-14. So this is carbon-12. If we were to write carbon-14, still has 6 protons because it's carbon. But now instead of 6 neutrons, we have a total of 8 neutrons. Radioactivity. So many nuclides are unstable and they spontaneously emit radiation, a process termed radioactive decay. This was first observed by Marie Curie. The intensity of the radiation is not affected by the temperature, pressure, or other physical and chemical conditions. When a nuclide decays, it emits radiation and usually changes into a nuclide of a different identity. And there are 3 natural types of radioactive emission. There's alpha particles, beta particles, and gamma rays. So alpha particles are essentially helium-4 nuclei, beta particles are electrons, and gamma rays are high-energy photons. This is a figure from your textbook, 24.1, just showing how these different particles behave in electric field. So when a nuclide decays, it forms a daughter nuclide of lower energy. So just like chemical reactions, nuclear reactions take place to decrease the overall potential energy of the system. And just like chemical reactions, we have conservation of energy. And that energy is carried off by emitted radiation and the recoiling nucleus of the daughter nuclide. So the decay process is represented by a balanced chemical reaction. Total reactants is equal to total products. So your mass number the total mass number will stay the same on both sides. And the total charge will also be will also stay constant. So Z, if we're talking about a nuclide, represents the number of protons, but it also can represent charge for some of these different decay processes. In the last lecture, I already mentioned the different types of radioactive decay, but let's just review them very quickly. There's the alpha decay. So radium can decay to form radon and emitting a alpha particle. Beta decay involves the ejection of a beta particle, which is essentially an electron, from the nucleus. So what happens in beta decay, a neutron is converted to a proton. So in this example, nickel is converted to copper. Nickel 63 is converted to copper 63 when a beta particle is released. Positron emission has the opposite effect of beta decay. So with positron emission, if a nuclide ejects a positron, a proton is converted into a neutron. So here we have the number of protons decreasing by 1 for positron emission. So this example of carbon 11 decaying to boron 11 is positron emission. Electron capture has the same result as positron emission. Both of them result in a proton being converted into a neutron. Electron capture is when the nucleus captures a low-lying electron, but they have the same effect on the mass number and the charge. So gamma emission involves the radiation of high energy gamma photons, and gamma emission usually occurs together with other forms of radioactive decay. So remember, we were talking about this conservation of energy. So in order for energy to be conserved, often gamma radiation will also be emitted. So several photons of different energies can be emitted from an excited nucleus as it returns to the ground state. Gamma emission results in no change of either the mass number or the charge, since gamma rays have no mass and no charge. This is just one more overview. This is a figure from your textbook that just shows alpha decay, beta decay, positron emission. So again, beta decay, a neutron's being converted to a proton. Positron emission, a proton's being converted to a neutron. And with electron capture, a proton is also being converted to a neutron. With gamma emission, we have an excited nucleus, and when it goes to a more stable state, a gamma photon is released. Okay, so let's just do a quick example of how we would write out a nuclear decay process. So we've got zirconium. Zirconium has 40 protons. It's a transition metal in period 5. And if it decays, if it undergoes electron capture, an electron has a mass number of 0 because the mass of an electron is so small relative to a proton or a neutron. So we're going to form some unknown element. But remember, the sum of A is going to be equal to the sum of A, and the sum of Z is going to be equal to the sum of Z. So here, the total mass number is 86 plus 0, so that's 86. And then the total charge is 40 plus -1, so that's 39. So now we need to look up what element has 39 protons. So we can rewrite this as yttrium 86. So often we want to be able to make predictions about what type of nuclear decay is going to take place. And to do that, we need to look at two main factors that determine the stability of a nuclide. The first is the ratio of the number of neutrons to protons. And the second is the total mass of the nuclide. If we plot the number of neutrons versus the number of protons for all stable nuclides, we can see a band of stability. So let's look at what that looks like. So this is the band of stability. So you can see on the x-axis, this is the number of protons. On the y-axis, this is the number of neutrons. And these are all of the stable nuclides. And I just wanted to mention that lighter nuclides are stable when your number of neutrons is equal to your number of protons. But as your number of protons increases, the N/Z ratio for a stable nuclide gradually increases. Something else that's very important is that all nuclides with more than 83 protons are unstable. Okay, let's talk about stability and nuclear structure. So first of all, protons within the nucleus experience electrostatic repulsive forces. Remember that if we have two charges that are the same, they're going to repel one another, and that's going to destabilize the nucleus. The strong force, which exists between all nucleons, counteracts the weaker repulsive forces. Nucleons are found in nucleon energy levels, and pairing of the spins of like nucleons leads to greater stability. So elements with an even number of protons usually have a larger number of stable nuclides. And over half of the stable nuclides have both even number of neutrons and an even number of protons. So here's just a few examples. So look at the elements that have an even number of protons. Cadmium has 8 stable nuclides, tin has 10, tellurium has 8, and xenon has 9. But now if we look at the elements with an odd number of protons, they have 2, 2, and 1 stable nuclides. So there is this increase in stability for when there are an even number of neutrons and an even number of protons. Okay, let's look at an example. So this problem says, which of the following nuclides would you predict to be stable and which would be radioactive? So remember that we said that an N/Z ratio equal to 1 is stable for the small nuclides. And when we're talking about small nuclides, we're specifically talking about Z less than or equal to about 20 protons. So anything calcium or smaller is going to follow this N/Z equal to 1. So in this case, Z is 10. This is neon. And our mass number, A, is 18. So our number of neutrons is 8 because 18 minus 10 is our number of neutrons, which is 8. So when we calculate this N/Z ratio, it's 0.8, which is less than 1. So this is not stable. Here, our N/Z ratio is less than 1. So that means that we have too many protons. So we need to convert a proton into a neutron. If you remember from when we were talking about different types of emission, positron emission would convert this from neon 18 into fluorine 18. So this is the radioactive decay that we would predict. Okay, let's look at this next one, sulfur 32. So Z is equal to 16. Your A is 32, so that means that N is also equal to 16. So here we have an equal number of protons and neutrons. So I would predict that this one is stable, and that's because sulfur is relatively small, whereas neon is unstable. Okay, let's look at this next one. So here we have thorium-236. Remember that anytime your number of protons is greater than 83, it's going to be unstable. So this is probably going to undergo alpha decay because any of our really big nuclides often will undergo alpha decay. Okay, and this last one, barium-123, got 56 protons, and your total mass number is 123. So your number of neutrons is going to be 123 minus 56. which is 67. Now this one's a little harder because it's hard to know where exactly in this band of stability we are at. So we do know that the bigger elements need more neutrons. This does have more neutrons than protons, but does it have enough neutrons? And the answer is probably not, because barium on the periodic table has an average mass of 137. So it's likely that barium-123 does not have enough neutrons. So again, we'll most likely this one will be unstable. Neutron rich, high over N over Z ratio, that's going to be beta minus decay. Proton rich, low N over Z ratio, that's going to be positron emission or electron capture. And for heavy nuclides, number of protons greater than 83, that's going to be alpha decay. Let's just do a couple more examples. So here we have boron 12. So we've got 5 protons. Our number of neutrons is 7. So again, this is too many neutrons. So when we have an N over Z ratio that's too high, that's neutron rich, that's going to be beta decay. So boron 12 will undergo beta decay to form carbon 12, which we know is a stable isotope of carbon. Uranium 234, again, Z is greater than 83, so this is going to be alpha decay. And there may be multiple different types of decay processes that take place for a particular nuclide. The way that we measure radioactivity is in a couple different ways, either an ionization counter. So ionizing radiation often accompanies radioactive decay, these gamma rays. So an ionization counter detects radioactive emissions as they ionize a gas. So the ionization produces free electrons and gaseous cations, which are attracted to electrodes and produce an electrical current. There's also a scintillation counter that detects radioactive emissions by their ability to excite atoms and cause them to emit light. So again, we're talking about these high energy photons and how they're either ionizing or exciting different materials. This is a argon methane ionization counter. So when a sample is decaying and those gamma photons are released, they're at a high enough energy to ionize the argon. So the electrons and the positively charged argon ions will be produced, and that will generate an electrical current. In the next lecture, we'll talk about the units of radioactivity.